So I can see the audience and I can hear you also. So, it would be nice to make this, for me, it would be nice to make this as interactive as possible. So please just blurt out any questions that you may have, and I'll try to take them online if I can. Oh, and I see there are more people coming in, so maybe I'll wait for a minute until everybody's, Yeah, so please feel free to ask any questions that you have as I go. Okay, so I'll start. The talk is called, the title of the paper is Monotone Additive Statistics. It's joint with Xiaosheng Mu, who's at Princeton, Luciano Pomatto, who's my next door neighbor at Caltech, and Philipp Strack, who's at Yale. Okay, so let me tell you what monotone additive statistics are. This might be a bit of a mysterious title. So what's a statistic? So I'm slightly misusing this word, but a statistic is some way of taking a distribution over the reals, a random variable, a distribution over numbers, and summarizing it by a single number. So for example, the expectation is a statistic. It's a way of taking a distribution and somehow summarize. It's something called a summary statistic, summarizing it by a single number. The median is another statistic. The variance is another statistic, right? So these are all ways of taking a distribution, each distribution, and assigning to it just one number. In economics, if we have a utility function u, which is, say, a strictly increasing function, then the u inverse of the expectation of u of a random variable x is again a statistic. It's what the agent would be indifferent between taking this deterministic amount versus taking the random amount x. It's a way of thinking of a whole distribution as just one number. In finance, the risk measures that have the same thing. So that's what I mean by a summary statistic, which I'll just call a statistic. Okay, formally, we're going to take some standard probability space, and we're going to denote by L infinity all the bounded random variables. So what's a bounded random variable? It's a random variable that never takes values bigger than some constant or less than some other constant. And L infinity are all bounded random variables. And a statistic is just a map that assigns a number is if I have a random variable, just a constant, I have a random variable that's actually not very random, it's just always the number 17, then this map is also going to assign to it the number 17. You can think about this as sort of a normalization. And if two random variables have the same distribution, then this map assigns the same number to them, right? So it doesn't depend on where in the probability space this random variable lives. It just depends on its distribution. You can also think about it as a map from boundedly supported probability measures to R. So for each probability measure, for each probability distribution over the reals, to each one of these, I assign some number. And the sort of things you have to have in mind is things like the expectation, the median, the variance, etc. Is this any questions so far?
The variance doesn't actually satisfy your definition.
Yeah, you're right. Because of the first condition. Yeah, so we're going to drop. You're right. This is a bit inconsistent, but the expectation and the median do. Let's erase the variance. I can't erase it with the mouse, but you're absolutely right. Okay, good. So that was a good question. Any other questions? Okay. Okay, so what's monotone? By monotonicity, I mean monotonicity with respect to first order stochastic dominance. So first order stochastic dominance is a partial order between random variables or between distributions, and it somehow captures the fact that one random variable, the mass of it, is to the right of the other one. So one formal definition is that x dominates y if the expectation of u of x is bigger than the expectation of u of y for every non-decreasing u. Other ways of thinking about it is that the CDF of x is everywhere lower than the CDF of y. If I ask, what's the probability that x is less than some number, this is always less than the probability that y is less than that number. Another way of thinking about it, maybe this is the most illustrative one, is that there exists some other random variables, x prime and y prime, that have the same distribution, But with probability 1, x prime is bigger than y prime. And the sort of picture that you should have, if you think of a random variable as a distribution of mass, if x dominates y, then I can start with y, push some mass to the right, and end up with x. And the statistic is monotone if whenever x dominates y, the statistic assigns a higher number to x than to y. Okay, so this is somehow a natural definition. You want to say if I'm going to capture a random variable by one number, if I just shift mass to the right, I want this number to weakly go up. And this again rules out variance, but it does, the expectation and the median, they both satisfy this. Okay, as do these sort of certainty equivalents. Okay, what's an additive statistic? Remember, we have monotone additive statistic. So what's an additive statistic? It's additive if phi of x plus y is equal to phi of x plus phi of y, but only for independent x and y, right? So this is our sort of main definition here. This is a very strong property, strong assumption, that for independent random variables, we want things to be additive. And the question of this paper is, what are the monotone additive statistics? For example, the expectation is one of them, but what are all the monotone additive statistics? That's what we're going to ask. Any questions so far? Okay, so let me tell you. Yeah, go ahead. Sorry, I can't hear a question. Oh, okay, no question. Let me talk to you a bit about this additivity assumption and in general why we might be interested in this. So imagine that we have a driver or maybe a self-driving car, an algorithm that needs to go from point A to point B, and it can either take the blue road or the red road. And let's say that this algorithm is only interested in getting there as fast as possible. So if the blue road takes more time than the red road, then great, we're going to take the red road. But in general, we don't know exactly how much time it's going to take. But we do have some distribution. We have some idea of the distribution of the amount of time that would take us to get from A to B on the red road, that we'll call X, and on the blue road, and that we'll call Y. And one way to sort of think conceptually of what an algorithm might do, an algorithm, just as a framework, there's no content in it yet, it would have some statistic phi, and it would calculate phi of x, calculate phi of y, and choose the lower one. So you want to think of phi of x as the deterministic amount of time that for me is equivalent to taking the red road, the road that takes x minutes to traverse, right? So this is some kind of index test. I'm going to assign a number to each random amount of time that I could take. And then when I have a choice, I'm going to choose the one where this number is lower. So if we're going to have some index like this, monotonicity is natural, right? If we're going to have something where I shift mass to the right, somehow this index should go up, right? If I have stochastic dominance, if x dominates y, then phi of x should be bigger than phi of y. But what about additivity? Why is that an interesting property in this context? So before you look at the claim, the idea is this. Imagine that after I go from A to B, I continue to C, and there's only one road from B to C. And so from B to C, the red and the blue roads coincide. And the amount of time it takes to go from B to C is Z, which is some other random variable that's independent from X and Y. Right? We have the traffic lights along X, the traffic lights along Y, and then we have what's going on along Z, whether there was an accident there. So Z is independent of X and Y. And the idea is that additivity corresponds to the decision of whether I'm going to take X and Y being independent of whether or not I'm going to continue afterwards to C. So if I just go from A to B, imagine I choose X, I should also choose X if afterwards I have to go from B to C. That's what additivity, and that's what this claim says. So this claim says, suppose that phi of X is bigger than phi of Y, implies that phi of X plus Z is greater than phi of Y plus Z for all Z that are independent of X and Y. Then phi is additive. It somehow means that if I add some extra noise or some things that happen in the future, that shouldn't change my decision now. So this is the sort of thing that additivity captures. If you want to think about this in the self-driving car algorithm context, if I tell the car to take me from A to B, it doesn't care whether afterwards I want to continue to C or not. It's always going to choose the same thing. That's what additivity, that's equivalent to additivity. So far, so good. Any questions? Okay. Here's another way to think about this. Instead of random time, we're going to think about this as random money. So we're going to have a bank, and this bank employs traders, and they have to make choices between investments. Trader one trades in the Chicago commodities market, and she trades pork futures. She has to choose between investing in X or an X prime. Trader two trades in cryptocurrencies and has to choose between Y and Y prime. You can see how old this presentation is. I did this before the crypto meltdown. I should update it. Now, the way these traders work, they just follow the rules of the bank. The bank says, here's how you should choose between risky, between different investments. And it's just an algorithm that calculates this phi. It's a definition of this phi. Whenever you have an X or an X prime to choose from, you calculate phi of X, you calculate phi of X prime, and you choose whichever one's bigger this time. And the CEO of the bank writes this manual, and she tells them exactly what phi is. The manual says I choose A over B if phi of A is bigger than phi of B. Now, the bank eventually, all these investments add up to the bottom line of the bank. So if trader one chooses X and trader two chooses Y, then the bank is going to get X plus Y. Now imagine that the CEO is worried about the following scenario. X and X prime, this pair is independent of Y prime. What happens in the pork futures market is independent of what happens in the cryptocurrency market. And imagine that trader one chooses X, trader two chooses Y, but X plus Y is stochastically dominated by X prime plus Y prime. So this seems undesirable. Somehow we've made these two independent choices, and we've ended up with something that's stochastically dominated by having both of them choose the other thing. And the claim says that if you want to avoid these kind of situations, you have to have a monotone additive statistic. In other words, if your statistic is not additive, you're going to be able to find such an example of X prime, Y prime, where you choose X and Y, but X plus Y is dominated by X prime, Y prime. So it's again about having independence between different parts of this. Well, okay, I don't know if again, this is about having independence between different parts of the system. If you have some kind of distributed system where different parts make autonomous decisions, then avoiding stochastic dominance in the aggregate is the same thing as having things be additive in the phi that you choose. Okay, so this was motivation. And now let me tell you the result. So before the result, let me give you some examples of monotone additive statistics. One that I already talked about is the expectation. The other one is the maximum of X. But what I mean by that is the maximum of the support of X. So these are bounded random variables. If I look at the highest possible value that X can take, this is a statistic, and this is going to be monotone and additive. If I shift mass to the right, the maximum can only increase. And if I add two independent random variables, the maximum of their sum will be the sum of their maxima, so it's additive. The same holds for the minimum of the support. If you're thinking about your statistic as capturing what deterministic amount of money a certain gamble is worth, if you think about this as a random amount of money, then if you go by the maximum, you're a very optimistic person who's sort of counting on getting the maximum payout possible. If you look at the minimum, you're somehow implementing the preferences of a very pessimistic person, very risk-averse person, who always assume they're going to get the worst possible outcome. In between those, you have these S sub A. So for any A that's different than 0, you can define this statistic S sub A that assigns to random variable X 1 over A times the log of the moment generating function of X, evaluated at A. So this is the cumulant generating function of X evaluated at A and normalized by 1 over A. The normalization gives us this property that when you put in a constant, you get a constant back. This is additive because the moment generating function of independent random variables is the product of their moment generating functions. Okay, so this monotone additive statistic SA, you can call it the normalized cumulant generating function of X, is a monotone additive statistic because we're integrating a monotone function here. And in fact, if you take this parameter A and take its limit as A goes to 0, you get the expectation. If you take its limit as s goes to infinity, you get the maximum. If you take its limit as x goes to minus infinity, you get the minimum. So if you let this parameter range from minus infinity to infinity, the closed interval, this really has all these examples. The question is, what else is there? So here's the result. The result is there really isn't anything else. Well, you can take convex combinations of these things, and you can take sort of weighted integrals, so weighted, infinitesimal convex combinations of these things. But the theorem says that if phi is a monotone additive statistic, then there's going to be some probability measure mu on this parameter A, so that for every random variable x, what phi assigns to this x is some kind of weighted average of what these SAs assign to this random variable x. Okay, so another way of thinking about it is that these SAs are the extreme points of the set of monotone. The set of monotone additive statistics is a compact convex set with the right topology, and these SAs are its extreme points. Everything else is just some kind of convex combination or limit of convex combinations of these SAs. So I'm out of time, so I don't really have time to tell you about the proof. Let me tell you about some extensions. You can imagine, wait, what if my x is not any random variable, but just a non-negative random variable? Or maybe it's an integer valued random variable, and you get the same result. You can imagine that you care about second order stochastic dominance, which I won't define, instead of first order stochastic dominance. You get the same result, but this measure mu has to be supported from minus infinity to 0, so it can't have any positive part. And you can say, okay, what if I care about unbounded random variables, say Gaussians? Well, you can slightly extend the set of random variables to those for which these SAs are finite for all A. So things that have sub-exponential tails. And then you get the same thing, except that this mu has to have compact support. Otherwise, this might be infinity for some random variable. So you basically get the same result even in this range. There's some related things, but not many. So people in statistic layman, they study monotone statistics, but not additive ones. In math, people like Rutza and Sekeli and Matner, they study additive statistics, but not monotone ones. There's some people in finance or in accounting that have similar results under weaker assumptions. So I don't want to go into it. And I want to mention another paper by some of us that shows that if you allow any random variable, so now we don't just allow random variables with sub-exponential tails, but take any random variable, it turns out that there are no monotone additive statistics. That's it. Thank you.
So I think we have time for one couple of questions while Federico will upload his slides. Any questions? No.
Okay, this is Bobby again. So for vector valued random variables, you still have these cumulants SA. A is now a vector. And I'm wondering if you know of a similar decision theoretic characterization of the convex hull of the SAs.
So this is our next paper that we hope to release soon. What you need to take is basically the same result holds. These SAs are going to be vectors, but you can't have mixed signs. So say in 2 dimensions, they have to both be positive or both be negative. And that's everything that you take. So very similar, the bottom line is something very similar holds in higher dimension.
So I have another question. Is it easy to see that the set of all monotone additive statistics is convex?
Convex, yeah, that's immediate.
Immediate, or why? Can you?
Well, if I have two monotone additive statistics, I take their convex combination. It's still going to be monotone because when I take the convex combination, each part will be monotone, and I'll still. I guess you just have to plug in the definition.